In this multiple degree of freedom system with multiple inputs, we are asked to construct its complete state space model. And we are after, in this example, just one output, the displacement of z, the bottom mass. So we want to find and construct the state space model. Now, this is an example where the state space model is probably going to be preferred over the transfer function. As we see, we have three input forces, F1, F2, F3, acting on the system. And usually for multi-input systems like this, the state space model is going to be a better representation. And when we get to the analysis portion, it's going to be easier to simulate the behavior of this system rather than trying to go to a transfer function model where it doesn't handle the multiple inputs as well. Multiple outputs is not bad, but multiple inputs it's going to have trouble with. So we have our mechanical system here made up of three masses. We have a node between spring K2 and damper B2 that is going to have its own degree of freedom. X, Y, P, and Z are all independent degrees of freedom. We can move any one of them independent of any of the other three. So we are going to end up having four free body diagrams, 3 for the masses and 1 for the node. So let's start with our free body diagrams step so that we can make our free body diagrams and use those to then write our equations of motion. At that point, then we will go on the actual state space modeling by transforming those equations of motion into the state space form. So in the free body diagrams, I am going to start at the top and work my way down. So I have M1 with, again, the given coordinate or degree of freedom x. And I will have its inertia on the right. So directly acting on M1, I am going to have that applied force F1. It's a function of t. I'll just have to remember that going forward. I won't put of t here because we're going to have a lot of things to draw and label. We have a spring force and a damper force, assuming tension. So in the spring K1, it is going to be put into tension when y is positive, but x is negative. So K1 times y minus x. And the damper B1 is going to have the same idea here. A positive y velocity will put it into tension, or a negative or upward x velocity. And then its inertia is going to be its mass of m1 times its acceleration of x double dot. And that's the complete free body diagram for the top mass. So working our way down, I'll do mass number 2. It has its own degree of freedom, y. And we can see the forces acting on it, and then the inertia. So acting on M2, we have the other side of K1 and B1. So those are, if we again assume tension, we already have those drawn and the values there. I don't have to do that a second time. That's the nice thing about kind of drawing this exploded view version of the free body diagrams. But we have a different input F2 acting on it, so I'll include that. And then directly touching M2 is spring K2, so assuming tension there, that is going to be K2, and I'll put this centrally. And K2 is stretched if P, the nodal displacement, is positive down, and Y is negative, so P minus Y for spring K2. And then this inertia is going to be M2 times its acceleration, Y double dot. And now we work our way down a little bit more because we can now do the node. So the node has a displacement P, and we'll stick with what is given, that P is positive down. So acting on the node is going to be this tensile spring force up. Again, we already have it labeled K2 times P minus Y, and then a downward force that we're going to see from the damper, and that is going to be B2 times the quantity of, here a positive Z dot, so a Z velocity down, we'll put it into tension, or a negative P dot. And then this is a node, so we are going to treat it as though it has negligible mass, which means it has no inertia, so nothing is happening on the right-hand side. And we have to keep going because we have a fourth free body diagram to draw of M3 with a degree of freedom Z down. So forces acting on M3, we will have the damper assuming tension, so that is pointing up and is already labeled. We will have F3 down, positive down. And here we have the spring force K3, and in this case, the bottom of it is touching the ground and the top of it is touching Z. So the ground is just going to be 0. So when Z is negative, K3 will go into tension. So I can write this as negative K3 Z. And then the inertia is going to be M3 Z double dot. So this gives us a lot of free body diagrams. We have a lot of variables to contend with. We have these 3 inputs, we have the inertias, but this is all of the free body diagrams we're going to need in order to derive our equations of motion in the end. So let's get to work in getting our, here, 4 equations of motion, 1 for each of these free body diagrams. So we can now start our equations of motion step. So equation of motion 1 will come from our top picture. So we'll sum forces in the x direction. So free body diagram 1, so sum of forces in free body diagram 1 in the x direction equals. So scrolling back up here, we have 3 forces acting. We have, I'll start with the spring and then the damper, and I'll put the forces last. So K1 y minus x. Also pointing down, we have B1 y dot minus x dot. Scroll back up and see that. So again, B1, that arrow is down along the x direction, so that quantity is positive. And then also down with the x direction is F1. So plus F1. So 3 forces equals our inertia. So here, M1 x double dot. That first equation of motion done. Now we can move on to our second free body diagram, which will be the second mass, which is going to have that y direction. We'll have 4 forces acting on this. So looking at the arrows, K1 and B1 are pointing up, so they are going to be negative. So I'll copy those first. So a negative K1, y minus x, minus a B1, y dot minus x dot. Going back to our picture, we have along the y direction the K2 p minus y, so that's positive. And also in the positive y direction, we have F2 pointing down. So that's along the y direction, so it's positive, and the inertia, the right-hand side while we're here, is going to be positive M2 y double dot. So equals M2 y double dot. In the third picture, we have the node. So we're looking in that P direction in our third picture. So here, in the negative P direction, we will have the K2P minus Y. So a minus K2P minus Y. But in the positive P direction, we are going to see that we have a positive B2 Z dot minus P dot. And those are the only 2 forces acting on the node at P. And equals our right-hand side. We have no mass, so the right-hand side in this case is 0. And equation of motion 4 coming from the fourth picture. In the Z direction, we will have a negative B2 Z dot minus P dot. We will have along the positive Z direction a negative K3 times Z, and then applied third force F3 equals m3z double dot. For equations of motion, a lot to write since we had those 4 free body diagrams. So now this is where we are going to actually start the state space modeling. We have our equations of motion. We don't do Laplace transforms. We need to identify our input variables, our state variables at this point. So let me just divide this out. I'm going to start with our input variables first. So that is going to be our u. And we have 3 inputs. We have F1, 2, and 3, so I am going to include them in that same order. So 1, 2, and 3. And these will be called, well, really U1, U2, and U3 in the state variable form. Right, so those inputs are determined. So now we need our state variables. So we have to, again, look at our equations of motion and identify these time-dependent variables that are not inputs. So F1, 2, 3 already in our inputs. So what do we have left that's time-dependent? We have the X family, the Y family, the P family, and the Z family. So we will include all of the X's or Y's or P's or Z's except for their highest derivative that appears in any equation of motion. So the order I put them in doesn't matter as long as I'm consistent. I'm going to put them in the same order as they were in the diagram. So going down, I'm just going to do it as the X family, the Y's, the P's, and the Z's, just to match the picture. But again, the order would not matter, X versus Y versus P versus Z, or where the derivative terms are. So let's look at the equations of motion. I have an X double dot. Therefore, X and X dot are state variables, so I'll include those. I have a Y double dot, so all but its highest derivative will be Y and Y dot. Those are included. And now this will be different than what we saw before. We have, because the node has no mass, there is no P double dot term. So the highest derivative is P dot. So when I include all but the highest value, or highest derivative, P is the only state variable. When we go back to Z, we do have a Z double dot, so its Z and its first derivative Z dot are state variables. Right, so we have X, X dot, Y, Y dot, P, Z, and Z dot. There is no P dot. It is not a state variable. In our equations of motion, P dot is the highest derivative term. So that is why P dot does not appear as a state variable. It'll show up when we differentiate X, but it does not show up yet. So I have an X1, an X2, 3, and 4, 5, 6. I have 7 state variables here. And now that I've put them in an order, I've assigned a number to them, X1 through X7. Now I can also list out the X dot. So that's going to be the derivative of each of my state variables. So I have X dot, X double dot, Y dot, Y double dot. Here's P dot, Z dot, and Z double dot. And these will also be known as then X1 dot, X2 dot, X3 dot, 4, 5, 6, and 7 dot. And again, I want to point out that this X underline, or it would be bold if I were typing it, the X vector is distinct from X, that scalar X. That scalar X is the position of mass 1. My vector X is my collection of state variables. So scalar X is an element of vector X, but they are not the same thing. With my inputs labeled, with my state variables labeled, now I need to go about and start rewriting my 4 equations of motion. So I'm going to start with 1. I'm actually going to first distribute my terms. So k1y minus k1x plus b1y dot minus b1x dot plus f1 equals m1 x double dot. Now I'll do my substitution. So that's k1y is also known as x3. k1x is also known as x1. Y dot is known as, well, looking over here, y dot is x4, but it is also x3 dot. So using the rule we've been using, I can express it as a non-derivative of a state variable, so I must. So that will be x4 minus b1 x dot, same thing applies, x1 x dot is x2 or x1 dot, so I will express it as x2, plus f1, which is also known as u1, equals m1, and now x double dot only appears as x2 dot, so I have no choice but to label it x2 dot. So that is 1a rewritten, I guess I'll call it 1b, now rewritten in terms of the state variables. So I've just replaced them all with state variables where I could, and the next double dot had to be replaced with x2 dot. So looking at the form of 1b, I was able to write this to have only one derivative term, x2 dot. So I want to rearrange this and solve it for x2 dot. So this is where I want to write my other side in numerical order of the x's and then the u's, and that's going to make it much easier when I go to finally write the big matrix at the end. So let's see here, my x1 term, I have only one of them, so that's negative k1 over m1 x1. I have a single x2 term, so I have a b1 over m1 x2. I have a single x3 term, so plus k1 over m1 x3, and a single x4 term, so b1 over m1 x4, plus 1 over m1 u1. And now 1c is complete. I have a full expression for x2 dot at this time. And I have grouped coefficients in front of my x terms and my u terms. In this case, they were fairly straightforward, but they'll get more complex as I get to the degrees of freedom that were neighboring other degrees of freedom. So let's look at 2a. So I'll take equation 2, and like before, I will first distribute all my terms. So negative k1y plus a k1x minus b1y dot plus b1x dot plus k2p minus k2y plus f2 equals m2y double dot. And let me just put a star so that when we come back, we have a lot of equations here. We remember which ones we are going to be using when we create our matrix. 2b, now I will substitute in my state variable names. So y is only x3, x is only x1, y dot, I'm choosing x4, and x dot is x2. K2p is x5. I have another y term as x3. And f2 is also known as u2. And m2, y double dot, my only choice is x4 dot. 2b, I was able to write with only one derivative term, the x4 dot. So that's good. I can isolate that, so I really want to divide everything by m2. Looking at what I have, going in numerical order, I have an x1 term, so that's going to be k1 over m2 x1. I have one x2 term, so I have a b1 over m2 x2. And let me start crossing things out as I go here, since I will have a bunch of terms. x3, I have two x3 terms, so I'm going to group those together. So minus quantity k1 plus k2 over m2 x3. X3 terms are taken care of. I have an x4 term, a minus b1 over m2 x4. So that is taken care of. And an x5 term, so a k2 over m2 x5 plus a 1 over m2 u2. And just make sure x5 and the u2 is done. All right, so that has taken care of 2b and gave me 2c, my expression for x4 dot. And I'll mark this one because now this one will be ready to put into my matrix going forward. All right, let's go to 3. And I'm going to make 3a from that. So distributing this, negative k2p plus k2y plus b2z minus b2p equals 0. As before, now I'll substitute in my state variables. P is x5, y is x3, z is x6, and this should be a z dot, and this should be a p dot from equation 3, and that is the case. So let me go back here. Z dot is x7, and p dot I can only call, it doesn't appear as a state variable, it only appears as x5 dot. So I have to rewrite it that way. All right, so 3b does look a little bit different, again, because it's that node. It looks different than what we saw in 2b and 1b. But if we look at it, it is still in a form that I want. I have only one derivative term, that x5 dot. So let me just rewrite this. I'm going to move it over just so it does look more like what we had before. So I move this b2 term over. Now it looks a little bit more familiar. So now when I go to rewrite it, I only have this one derivative term x5, so I want to isolate it. So in order here, I am going to have a k2 over b2 x3 minus a k2 over b2 x5 plus a b2 over b2 x7. So that actually will just go to 1. And that's my x5 term. That will go into my states, into my matrix when I get to that point. All right, closing in on it for A. Actually, I have to scroll up for this one. So I want to take 4 and distribute it out. So I have here negative b2z dot. And that will be then a plus b2 p dot after I distribute it. Negative k3z, that's fine as it is. I have then plus f3. And that equals, back to the right-hand side, m3z double dot. Same pattern as before. Let's put in our state variables. Z dot is x7. And that's just x7 plus p dot, or b2 p dot. P dot only appears as x5 dot. I have no other choices in that matter. Minus k3 times z. Z is going to be x6 plus u3 equals m3. And here z double dot only appears as x7 dot. No other choice for that. Looking at 4b, I have a slight problem in that if I look at what's going on here, I have 2 derivative terms. I did not see that in 1b, 2b, 3b, or the previous examples here. But I need to be able to express this as just a single expression with one derivative term. So the fact I have x5 dot and x7 dot is a problem at the moment because there's 2 derivatives. I want only one. However, this can be remedied because actually I can replace the x5 dot term. I actually already know another expression for x5 dot. That is equation 3c. So I can just substitute that in, and if we look at 3c, the right-hand side has only x3, x5, x7. It has no derivative terms. So I'm going to be able to eliminate one of my derivatives, x5 dot, by substituting in 3c. And I can get in, I guess I'll call it 4c as I go forward using that substitution. So this will be negative b2x7 plus b2 times, and I'll just put in this whole thing for now. Plus x7, and then minus k3x6 plus u3 equals m3x7 dot. Okay, so I've eliminated one problem here. I now have just an x7 dot, and that's the only derivative term, so that's good. I'll do a little bit more algebra as I keep going. So I'll distribute this through, so the b2s are going to cancel, so I have a k2x3 minus these b2s cancel, k2x5 plus b2x7 minus k3x6 plus u3 equals m3x7 dot. And finally at 4e, now since I have only that one derivative term, I can isolate it. So I have x7 dot equals. So let's see what I have on the left-hand side here. I have an x3 term, so k2 over m3x3. That's taken care of. I don't have an x4. I do have an x5 term. So a minus k2 over m3x5. I have an x6 term. So minus k3 over m3x6. That's taken care of. And then I have a negative b2x7 and a positive b2x7. So x7 actually is going to cancel out. And finally, I have a 1 over m3u3. And that, 4e, now has x7 dot isolated. Okay, so all of the equations of motion, all four of them have been rewritten, and we have then 4 of our expressions, but we actually need 7 because we have 7 state variables. So we need an expression for x1 dot through x7 dot. And so far we have x2 taken care of. We have x4 dot, or x2 dot, x4 dot, x5 dot, and x7 dot. So we still need a fifth equation. Well, we'll need several more because we need an expression for x1 dot. That has not yet been isolated. We're going to get these from the mapping equations. x1 dot I can express as x dot from the lower equation. X dot is also x2, therefore x1 dot is also x2. Okay, we have x1 dot, we have x2 dot, we don't have an x3 dot yet, so that needs to come into play here. So x3 dot, again from a mapping equation, x3 dot is y dot is also x4. So therefore x3 dot is also x4. And the final mapping equation, I have now 3, 4 I already had into C, x5 dot I have an expression for, x6 dot I still do not. So I need an x6 dot expression. So coming from mapping, x6 dot is z dot is also x7, so x6 dot is also x7. So now these, again right away I'll put a star there, these 3 are also going to go into our matrix form equations, which now we are ready to write. So all of this, we finally have the 7 equations. We have an x1 dot expression through an x7 dot expression done. 3 from mapping equations and 4 from our equations of motion that came from our 4 free body diagrams. So now we have to transcribe all of this. So we're ready to start putting it into our state equation here. So x dot equals our A matrix. Our A matrix is going to be 7 by 7 because we have 7 state variables. So it's going to be a lot to fill in. So I'll create some room, but let's see how big this is. So the first line of this is my x1 dot expression, which that's my equation 5 here. So that's going to be 0. I'll leave myself a lot of room. 0, 4, 5, 6, 7. And this will get multiplied by my x, which is x1, 2, 3, 4, 5, 6, 7. All right, first row is done. And then we're also going to have our B matrix. I'm going to have to come back to that since these are just very large. So I'll just fill out A first using my x1 through 7. Second row comes from x2 dot, which was our equation 1c. So I have an x1, 2, 3, 4 here, and then I'll come back to get the B later just so I can see it all at one time. So taking off the coefficients, I have a negative k1 m1, I have a negative b1 over m1, I have a positive k1 over m1, and I have a positive b1 over m1, and then zeros for the rest of them. So again, let's look at equation 1c. Those are the coefficients in front of x1, 2, 3, and 4. And then 5, 6, and 7 are 0. They're not written here. Now I'll come back for that 1 over m1 for u1. My x2 dot equation is done. My x3 dot equation is equation 6. So that is x4. So 1, 2, 3, 4, 0, 0, 0. Now my x4 dot equation, which is coming up here, equation 2c. So I want to pull off these coefficients and then transcribe them into my matrix. So I have here a positive k1 over m2, a positive b1 over m2. I'll have a negative k1 plus k2 over m2. Scroll back up for the x4 dot equation. All right, so 1, 2, and 3 are taken care of. 4 is negative b1 over m2. The x5 equation then, or the x5 expression, k2 over m2, positive. And zeros. All right, so x1 dot, 2 dot, 3 dot, 4 dot, my x5 dot equation, that is from equation 3c. So I have a 3, a 5, and a 7 there. So nothing for x1 dot, or for x1, nothing for x2. I have a k3 over b2 in front of the x3. I have a 0. I have a negative. Just double check these for x5 dot. So k2 over b2, that should be a k2. And this is a negative k2 over b2 in front of 1, 2, 3, 4, x5. Let's just double check that here. And yeah, negative k2 over b2, x5, and then it just turns out to be a 1 in front of the x7. So 0 and 1. That was my x5 dot. x6 dot is equation 7. It's just x7. So next row, zeros, and a 1 at the end. And finally, my x7 dot equation, and that is coming from equation 4e. I have an x3, a 5, and a 6 to transcribe down. So 0 in front of x1 and x2. I will have the positive, scroll back up, k2 over m3. I have a 0, a negative k2 over m3, and double check that. That should be in front of my x5 term, right? k2 over m3. I also have a negative k3 over m3 in front of x6. This is a k3 instead of a k2, k3 over m3, and x7 does not appear. So try to take this entire matrix in at once. This is the A matrix. All right, so we can fit it all here. So let me label this because it's large. This is a big system. That's my A matrix. Now, I still have to do the B matrix. Unfortunately, that one will go a little bit quicker. But A is 7 by 7 because I have 7 state variables here. So A will always be a square matrix, and it is. Let's look at the B matrix. So this will be plus our B matrix times U. Start it down here. All right, so this will be quicker to do, but same thing, let's go back to those equations. The x1 dot equation had no u1, 2, or 3 in it. And I'll point out that we already know the size that B should be is the number of rows equal to our number of state variables by the number of inputs we have. We had 3 inputs, F1, 2, 3, which we called U1, U2, U3. So very important to note the size of B. It is not 7 by 1, it is 7 by 3. So first row, we have no U terms, so all zeros. X2 dot. Going all the way back up to 1C, we have a U1 term. 1 over M1 is its coefficient. So coming down here, 1 over M1 times U1, 0, 0. X3 dot. There are no U terms, so all zeros. X4 dot. We have equation 2C. We have a 1 over M2 in front of a U2. So 0 for the U1, 0 for the U3, 1 over M2 for the U2. X5 dot is equation 3C. There are no inputs there. There's no U term in that expression, so a row of zeros there. X6 dot is just X7, so that's another row of zeros. And my X7 dot equation coming up in 4E, I have a 1 over M3 times a U3. And no U2, no U1. Yeah, so let's look at this B all at once. So this is my 7 by 3 B matrix. Notice, again, 3 columns, 7 rows, and we got these also from the 4 equations of motion, 3 mapping equations. Now, normally I would write this all on one line. It's just that these are very large and just don't all fit together. But this is that state equation, that x dot equals ax plus bu. And that's what I have here. Again, remember that u, just since we haven't seen a multi-input one before, u was equal to u1, u2, u3, which corresponded to f1, f2, f3. All right, so we have those big matrices done. We still need our observation matrix or our output matrix y. Let's go all the way back and see what are we trying to find here. Our one output that we wanted to track here was the displacement z. So going all the way down here, our observables y bar, vector y, for this problem is just z. And z, if we go back up here, z was x6. I'll put it in the matrix here, even though it's just a single value. Okay, so our observation equation is in the form of cx plus du. So the c is going to have as many rows as we have observables. In this case, 1, or outputs, which is 1, z. It has as many columns as we have state vectors, or state variables, which will be 7. Plus d is going to be the number of observables, 1, by the number of columns is going to be the number of inputs we have, 3. So let me mark that. So C, we know, is 1 row by 7 columns. And D is going to be 1 by 3. Right, so again, 1 row in each because we have one observable, namely Z, also known as x6. C is 7 columns because we have 7 state variables. D is 3 columns because we have 3 inputs. And that gets multiplied by the U. All right, so now we can fill in the details. Well, how do we get this Cx plus du to be just x6? Well, it's 1, 2, 3, 4, 5, 6, 0. That will pick out just the x6 from my x vector, and u doesn't appear. So D will again be a zeros matrix or a zeros vector, but the size of it still is going to be important. We have to make sure it's a 1 by 3. So with that, we have our observation equation, our y vector equation. We have our x dot equation from above. So we have our complete state space model. It's a lot to take in, but that is the complete state space model for this particular system, this multi-degree of freedom system with 3 inputs. So let's review how did we get to our complete state space model here. We started with our mechanical system diagram. We saw that we had 4 independent degrees of freedom, x, y, p, and z, that were attached to 3 masses and 1 node, the node at P between spring K2 and damper B2. So each degree of freedom had its own free body diagram that we drew out here that had all of the degrees of freedom attached to it and the inertias. We used the 4 free body diagrams to derive 4 equations of motion, just as we've done before with mechanical systems, and whether this were going down the route of being a transfer function model or here the state space model, up to this step would be exactly the same. We need those 4 equations of motion to go forward with either modeling method. Since we are doing state space modeling for this one, we take these 4 equations of motion and identify all of the inputs. This system has 3 inputs, the 3 forces F1, F2, F3. So I named them in the state space form U1, 2, and 3. For simplicity, I'm doing them in numerical order. Now we have to look at these 4 equations of motion and identify our state variables. So again, looking at dependent variables, so variables of time or dependent on time, we want to include all but the highest derivatives of those variables. So F1, F2, F3 were inputs. They are not going to appear here, but we have x's, x dot and x double dot. We have y's, we have p's, and we have z's. Our highest derivative term for x is x double dot. So x and x dot were state variables because it's all but the highest derivative. Y double dot was the highest, so y and y dot. Here's where we saw something different than previous examples. P dot was the highest derivative of p, so p itself was the only state variable in the P family. Back to Z, we have a Z double dot, so Z and Z dot were both state variables. I decided to order these in the same order as the diagram, going from X to Y to P to Z, and once I establish that order, I have to stick with it so that all of my matrices are going to be consistent with this definition of X1, 2, 3, 4, 5, 6, and 7. With the state variables named and allocated and decided their order, I can find the x dot, so it's just the derivative of each of those state variables. Now my job is to go back through my equations of motion and rewrite all of the time-dependent variables, inputs and outputs, in terms of the state variables and the input variables. This one took a little bit more algebra than other ones did, but we saw that we were able to get a single derivative term isolated in 1C and 2C. We had a bit of and in 3C actually, because x5 dot was by itself. So actually a little bit of an issue came in 4B. We have, which we didn't see before, an x5 dot and an x7 dot. We didn't do anything wrong. It's not that we named something as a derivative term that we could have named as a non-derivative term. We could have only called p dot x5 dot. We could have only called z double dot x7. But in this case, we previously already solved for x5 dot. So I substituted in that right-hand side in 4b to write 4c. So the problem is solved in that we now have only a single derivative term, x7 dot. So I went and isolated that, and now I have 4 equations for 4 of the state variables, or derivatives of my state variables. For the other 3 equations, since I needed a total of 7, 1 for each state variable, I had 3 mapping equations, and this is recognizing, again, the relationship between like x and x dot. Since x1 and x2, we have to tell the system they are related. x2 is the derivative of x1. The same idea for x4 and x3, and x6 and x7, or x7 is the derivative of x6. So that's what the mapping equations are establishing, is that they are state variables that have a dependence on each other, or their derivatives have a dependence. I took those 7 starred equations here, the 4 equations of motion, 3 mapping, and transcribed them into my matrix form for my state equation, so my x dot equation. So I made my A matrix, which gets multiplied by x. Those are the coefficients in front of x1 through x7. And then the B matrix, which is 7 by 3 for this example, because I have 7 states and 3 inputs, and those were the coefficients in front of u1, u2, and u3. So that was my entire state equation. Then my observation equation, or my output equation y. We were told in the problem that we have one output that we were tracking, the displacement z, and that is all. So a single output. In state variable form, that was just simply x6. So now I have to complete my C matrix and D matrix, because I know that y, or vector y, is cx plus du. I know that the C matrix is the number of observables by the number of states, so 1 by 7, 1 observable. And D is going to be a matrix that's the number of observables by the number of inputs, 1 observable by 3 inputs. So in order for this right-hand side to be equal to x6, then C has to be all zeros except a 1 in the 6th position to pull out that x6. And D has to be all zeros because there is no U expression in the output that we are tracking. But we do have to preserve the correct sizing for C and D so that the linear algebra is going to work out correctly.